This summer I worked on antibody shape refinement project in JetBrains research. My name is Ekaterina and my mentor is Natalia Zenkova. So let's start by looking at antibody and what is it? So antibody is a protein that identifies viruses or other pathogens in organisms and neutralizes them. The common name for viruses is an antigen. So the antibody binds antigen via specific sites. And these sites are variable and specific for different antigens. On the ends of the antibody, there are loops that are responsible for that binding. And in the field of antibody shape refinement, most of the loops do not pose problems except one region, CDR-H3. This is complementary determining region on heavy chain loop 3. And it is the most variable region across different antibodies, hence it's more difficult to accurately predict it. And this is the goal of this project, to predict this region. So basically, we're going from amino acid sequences to 3D coordinates. So let's first talk about data. For the training, we need sequences and coordinates of the 3D structure. The data was taken from SAFDAP database where antibodies are gotten from X-ray crystallography analysis. And we did several preparation steps. So selecting unique sequences so there won't be any duplicates, filtering by organisms, and choosing antibodies only bound to antigens. So as pre-processing steps, sequences are transformed to embeddings to have meaningful representation. We used ALMA embeddings. However, during the process, we found a problem that for the same sequences, it produces slightly different embeddings. And it posed a problem actually because the model was written to exclude non-unique sequences based on the embeddings. So we changed it and now we removed by sequences. Next, we're looking into organisms to which antibody belongs. We decided to remove some organisms not related to production, as antibodies from other species can differ from target. So basically, if you want to actually produce antibodies for some treatments, you need to pay attention to what organisms are used. So if you want to produce it for human, you want to look into human or mouses on which you are going to be testing the drug and similar organisms. And there is another criteria, binding with antigen, as I talked with previously. Antibodies from database were visualized either when they were bound to antigen or not. And it can actually affect the structure as when antibody is free. So as seen in this picture, the purple part is the loop that we want to predict, and it is not bound to antigen. So when it is free, it can be close to some different structures, to different antibodies, and it can actually affect its conformation. And this was proven in the article mentioned here. So we're thinking about end-to-end solution for production, and that's why we chose antibodies bound to antigens, as this is the confirmation that we want to get in the end. Moving on to the model already existed previously in this project. It is based on bidirectional LSTM, but we did some changes there. Firstly, as an introduction, as I understand, not everybody knows biology here, torsion angles are basically rotation angles for bonds between specific atoms in the backbone of proteins. And previously, the model predicted something like this. Like in this picture, green and purple are predicted structure and target structure. So even though the shape of the loop is close to the target, it is a bit distant from it because of some wrongly predicted angles. And that's why we decided to consider torsion angles in our model, and we included it into a loss. So our loss consists of flat angles, which is what you think about when you just talk about angles, the distance loss and the torsion angles loss. And torsion angles losses simply just mean squared error, like L2 loss between predictions and target torsion angles. We also did some modification and research and evaluation metrics. The commonly used RMSD metric has some drawbacks, but still is used for comparison, as most of the projects use that. And we found two other metrics, global distance test score and template modeling score. They are more sensitive to global similarity rather than small error, which makes it more accurate in comparing similarity rather than RMSD. And additionally, it is also length independent. So we implemented both of these metrics to evaluate our model. And another metric on which we want to compare is time. So we compared it to two state-of-the-art models, DeepH3 and DeepAB. And even it depends on some factors like the length of our data, what we choose, but overall it can be 10, 20 times faster in training, and while not really losing in quality. For testing time, it's a bit harder to compare, and testing time is very important because if you want to use it in production, you don't want to wait for days for your prediction, right? So our model can actually predict one structure in less than a second, and we can't really compare it to those methods mentioned because they're not end-to-end, meaning they're not actually producing coordinates while we are, so our method is end-to-end. And to compare with those state-of-the-art methods, there is an antibody benchmark data set provided by them. However, it has drawbacks as there are only 49 structures and they are with and without antigen, which is not included in our data. So just evaluating our model on this data set is not really reliable. And for our plants, we want to also add weights to our loss so it can be more accurate. And probably the torsion angles loss will have the highest weight, but we'll see about that. And we also want to create a new benchmark data set which can be more reliable. And we want to write a paper for machine learning for structural biology workshop.